Alright, here we go. This is lesson 5-1 in your Trig textbook, the notes for my class. This chapter covers trigonometric identities, all kinds of trig identities. It also covers sum, difference, double, and half angle formulas, which we have not covered yet in class, but we will. So these notes are introducing us to the idea of what an identity is and what we need to do in order to verify them. So, section 5.1 is entitled Fundamental Identities, and we are talking about this idea of a trigonometric identity. A trigonometric identity is a trigonometric equation that is true, satisfied, equal, for every single value of the variable. In most cases, that variable will be theta. Again, it is commonplace for us to use theta as the variable when we're representing an angle, and trigonometric functions deal with angles. Now, we've already talked about quite a few trig identities in this textbook. So what I've done is I've pulled the pages from those earlier lessons and placed them into this lesson so that we can quickly review them and have them all in one place. So we've basically talked about 4 or 5 sets of identities. Some of them are more important than others. The first set of identities we've talked about are the reciprocal identities. That is that sine of any angle, sine of theta, is equal to 1 over the cosecant of theta. The cosine of any angle is equal to 1 over the secant of that angle, and the tangent is 1 over the cotangent. Each pair of these trig identities are reciprocals of each other. So sine and cosecant are reciprocals, and cosine and secant are reciprocals. Now, it's worth noting that with any trig identity, these are equations, which means they have multiple forms. We are allowed to manipulate them just like we do any algebraic equation. So if we wanted to, we could multiply both sides of this equation by cosecant and receive the equation sine theta cosecant theta equals 1. We could do the exact same thing with these other two equations. So if we wanted to, we could write those in a different form. We could multiply both sides by secant theta in the second one, which would give us cosine times secant equals 1. We can do that with cotangent in the third equation, which would give us tangent times cotangent equals 1. And that might occasionally be useful to us. In addition, we could also switch which one of our expressions is by itself. Simply by dividing this by sine theta, we could get the version that says the cosecant of theta is 1 over the sine theta. Same thing here with cosine. If we divide both sides by cosine, we can get that the secant of theta is 1 over the cosine of theta. Same thing here. If we divide by tangent, we can get cotangent is 1 over tangent. I screwed that up pretty royally there on my symbols, so I'm going to erase real quick and fix it. Cotangent of theta is 1 over tangent of theta. Now, as for which versions we use the most often, we usually use these two identities extremely often in the processes we're going to talk about in the first 2 sections of this chapter. That is that cosecant is 1 over sine and secant is 1 over cosine. So you need to know that those two are going to be more important most of the time than the other forms of these reciprocal identities. It would probably behoove you, be good for you, to memorize those identities. The second set of identities we talked about, and I realize there's a lot going on this page, but this again is copied directly from the earlier lesson where we derived these identities, are called the Pythagorean identities. Pythagorean identities. They're based on the Pythagorean theorem. The first one of those that we came up with was cosine squared plus sine squared is equal to 1. that is going to come up extremely often. So again, if you're looking for which one are we going to use more often than the others, it's going to be that one. We're going to use that a lot. Okay? Keep in mind that just like the other expressions, we can rearrange that equation. Oops, that's not my pen tool. And we can say, subtract sine squared from each side, and that would give us cosine squared is 1 minus sine squared theta. Or we could subtract cosine squared from each side, which would give us sine squared theta is 1 minus cosine squared theta. All three of these expressions are exactly the same. They're just different forms, just like on the previous page where we had different forms of our reciprocal identities. We do that same process we used to derive that. We divide by a different term, and we derive two other Pythagorean identities. 1 plus tangent squared is equal to secant squared. And again, we could rearrange that into a couple of other forms if we wanted to. We could make that into tangent squared equals secant squared minus 1. Or we could make that into 1 equals secant squared minus tangent squared, simply using some algebraic manipulation. Same thing for this last expression, cotangent squared plus 1 equals cosecant squared. We could do the exact same thing we did before, and we could change that into cotangent squared equals cosecant squared minus 1. Or we could change it into 1 equals cosecant squared minus cotangent squared. So keep in mind that each of these can be rearranged using basic algebra anytime we need to fit our situation. The third set of trig identities that we use quite often are the quotient identities, and these are the ones that relate tangent and cotangent to sine and cosine. Again, this is the page from earlier in the notes, probably chapter 1 or 2, where we derived what tangent was in terms of sine and cosine. That is that tangent theta is sine over cosine. We can also do that the opposite direction to get that cotangent of theta is cosine over sine. So these two are our quotient identities. You're going to use these all the time in the process that we're talking about in this chapter. All the time. So again, these two are going to be extremely important. Okay? My highlighter just did all kinds of crazy things there. So let's see if we can get it to behave long enough to get a good highlight on that. There we go. So again, those two are very important, and you need to be aware of them. So hopefully all of those are now in one set of notes for you to use. Now, in addition to that, we had a couple other sets that we talked about that are of far less importance. And in this section, we start talking about this idea of a negative angle identity. Now, when we're talking about an angle, and that angle is in standard position, we have to remember what that means. Okay, an angle drawn in standard position, I'm over here on this picture over here, will have one side attached to the positive x-axis, and when we rotate in a positive direction, we would get an angle theta. So let's say this is angle theta. Okay? We know that this point, located on whatever circle this point as it rotates, this point will have coordinates of cosine theta, sine theta, assuming, of course, that we've set our radius equal to 1 unit. Okay, so from here to here is 1 unit. Okay? Actually need that out of the way though, so I'm going to erase that now. Okay, so the radius of this circle is 1 unit, just so we're aware. Okay? On the other hand, if we want the negative version of that angle, it would still start on the positive x-axis, but the rotation, instead of going counterclockwise, would be clockwise rotation. So that would be negative theta. Well, that angle right there, that point, is going to have the same coordinates, except since we're in the third quadrant, cosine will be negative and sine will be negative, right? Actually, no. The cosine would be the same because cosine is your left and right, sine is your up and down. Again, that's from earlier in the notes. So what happens is we can relate negative theta to positive theta through each of our 6 trig functions. For instance, the sine of negative theta down here is the opposite of positive theta. Cosine, on the other hand, which is the x value for each of these points, would be the same, which tells us that the cosine of negative theta is simply the cosine of theta. Notice I did not write a negative sign there. Now, if we use sine and cosine to derive the other trig functions using our reciprocal and quotient identities, we would get that the tangent of negative theta is equal to negative tangent of theta. The cosecant of negative theta, which is the reciprocal of sine, would be equivalent to the negative cosecant of theta. The secant of negative theta is simply the secant of theta because, again, secant and cosine are reciprocals, so they would follow the same rules. And finally, the cotangent of negative theta is negative cotangent of theta. This is going to be a situational set of identities. We're not going to use them all that often. But notice that cosine and secant have the same secant value, the same cosine value, whether the angle is positive or negative, whereas the other 4, you'll notice I wrote them in red, have the opposite value. So the first thing we're going to do is use one value to find other values. So if we look here, we're told the tangent of theta is negative 5/3 and that the angle theta ends in quadrant 2. We're asked to find the value of secant. So what we need to remember, or what we need to do to start this kind of problem, is we need to come up with an identity that relates tangent and secant. So we would go into our notes and we would look for a trig identity that only relates, so we would say, what trig identity, so what we're saying to ourselves, relates only tangent and secant. And as we look through our list, we should come up with tangent squared theta plus 1 equals secant squared theta from our Pythagorean identities list. And that is where we should start. Now what we do is we substitute negative 5/3 from the directions into the problem for tangent. So we would have negative 5/3 quantity squared plus 1 equals secant squared theta. And we would simplify that. So when we square negative 5/3, we would get 25 over 9, to which we would have to add 1. Remember that 1 is really 9/9, because we'd have to get a common denominator, so we'd multiply the bottom and the top by 9, which means that 34 over 9 is equal to the secant of theta, secant squared of theta, sorry. And then to get secant, if we need to get rid of squared, we take the square root. So that would tell us, move up here, that the secant of theta is either the positive or negative square root of 34 over 3, because we take the square root of the top and the square root of the bottom. Root 34 does not reduce. The square root of 9 is exactly 3. Now this is where the rest of the directions come into play. Okay? We have to deal with this plus or minus symbol. That's a problem. Let's try to pick a color that isn't so overwhelming. But they told us theta is in quadrant 2. So we have to go back into our reference items and we have to look up what the sine of secant is in quadrant 2. Secant is related to cosine. So in quadrant 2, secant of theta is always negative. Always negative. So we would say in this case that the secant of this angle theta, whatever it is the negative square root of 34 over 3. That takes care of the first part of this problem. Okay, so then we move to part B. Notice that the tangent of theta is still negative 5/3. That's the same as the previous part. Theta is still in quadrant 2, which means we already know that the secant of theta is negative root 34 over 3. Now, whether or not we're going to end up using that really depends on how this plays out, but it's information that we know, so there's no reason to discard it. Okay, so we're asked to find sine. So we think to ourselves, is there a trig function that relates sine to only tangent? And sadly, the answer to that is no. However, there is a trig identity that relates tangent to sine and cosine, right? Well, we don't know the cosine, but we do know that the cosine of an angle is the reciprocal of the secant. Which means if I flip the secant over, that would be the cosine. Now, mathematically speaking, we're not allowed to leave that with a root 34 on the bottom, so we have to multiply the bottom and the top by the square root of 34 to rationalize the denominator. That is an Algebra 2 lesson, which would mean that the cosine is equal to negative 3 root 34 over 34. Once we have the cosine, we can relate the sine to the tangent through cosine, because the tangent is the sine divided by the cosine. If I want to solve that equation for cosine, that's very easy to do. I just multiply both sides of that expression by cosine theta, canceling it on the right side, and giving me the expression sine theta is cosine theta times tangent theta. I know both of those values, so all I have to do is plug them in and simplify. So the cosine from my side work over here is negative 3 root 34 over 34, and my tangent is negative 5/3. So I would multiply those values together. When I do, the 3's are going to cancel, as will the negatives, because negative times a negative is a positive, and give me 5 root 34 over 34. You can put that in the calculator if you want to. Finally, third part of this problem is asking us to find the cotangent of negative theta. Well, this is actually the easiest one yet. First thing we need to do is apply the negative angle identity for cotangent, which says the cotangent of negative theta is the negative cotangent of theta. Again, that was that last set of identities, the only new ones for this section. If you go back and look, it's the very last one on that list, number 6. It says the cotangent of negative theta is the opposite of the cotangent of theta. Now the cotangent, that is the reciprocal of the tangent. So if we know that tangent theta is negative 5 over 3, then that means that cotangent theta is negative 3 over 5, the reciprocal of what they gave us in the directions. The two negatives would cancel each other out. telling us that the cotangent of theta, or negative theta, the cotangent of negative theta, what they asked for in the problem, is equal to 3/5. That would be the answer to the question, because those two negatives would cancel, leaving 3/5. Okay, now the big skill here in lesson 1 is preparing us for verifying trig identities, and that is to take expressions made up of trig functions and simplify them so that they do not contain any quotients, those are division signs, so no fractions, and that all of the functions are only in terms of theta. That means no negative thetas. We're also going to try to simplify as much as we can. However, on occasion, it won't really get much better, and the big difficulty here is knowing when we're done. This situation will be made much better in the next section when we're actually verifying and they give us both a starting and ending point. So, start off with, we're going to do quite a few of these as well because this is such a key skill, and unfortunately it's not a very easy skill. So we'll go through quite a few of these. We'll start off easy, we'll build up into some hard ones, and then at the end we had a couple that I asked you to do on your own, so they'll actually be a little bit easier. So the basic approach that we're going to take is we are going to turn every expression in this entire statement and turn it into sine and cosine. For instance, cotangent of theta can be written as cosine over sine using one of our quotient identities. So we would write this expression and we would say that's equal to cosine theta over sine theta times sine theta. Well, when we do that, our algebra brain should kick in and say, oh, I've got a sine on the bottom, a sine on the top, those will cancel, which means that this expression is equivalent to cosine of theta, which is a simpler version of the same statement. Let's do another one. Okay, this one's pretty similar. We have 3 this time. So we go and we look up the values to turn everything into sine and cosine. Secant of theta can be written as 1 over cosine. Cotangent we just dealt with on the last problem. That's cosine over sine. And we're not going to do anything with sine because it's already in terms of sine and cosine, so why mess with a good thing? So that would be 1 over cosine times cosine over sine times, and we left sine alone. And again, our algebra brain should kick in and go, hey, look, there's a cosine on the bottom and the top. That cancels. Hey, look, there's a sine on the bottom and the top. That cancels. So all that I have left here is 1. Should be a much simpler version of the same statement. Okay, so again, this is one that you tried on your own the day that we did these notes. So again, I'm going to go pretty quickly through this one. You should recognize that cosecant can be written as 1 over, it shouldn't say equals, 1 over sine. But you're thinking, hey, that didn't cancel. You're right, it didn't cancel. But that's okay. It's not always going to cancel. But, using what we know about fractions, if I multiply 2 fractions together, and yes, this is a fraction, it's cosine over 1, I multiply across the top and across the bottom. So that would give me cosine over sine. Cosine over sine is cotangent. So all this stuff I'm writing in green is the stuff that you should be realizing and putting in without actually having to write it. It's the stuff that should just be going in your brain and going, oh yeah, I have that on that other page. I see that. So my answer there would be cotangent. Moving on. Okay, so here's the first one we've seen that contains any exponents. This is actually something that comes up all the time. It's not even rare. Hopefully, we would realize, based on what I said earlier when we went back through our identities, that cosecant theta minus 1, cosecant squared theta minus 1, was one of our versions of our final Pythagorean identity, and that equals the cotangent squared. So I would replace that with cotangent squared. That would be my first step. So I would have sine squared theta times, and now I would have cotangent theta. Then I would want to replace cotangent theta, or cotangent squared theta, using the fact that cotangent is equal to sine over cos, or cosine over sine. And I would say I have sine squared theta times cosine squared theta over sine squared theta. My algebra brain should kick in, canceling the sine thetas, and leave me with cosine squared theta as my final answer. Okay, so here's another problem that we're going to see on occasion, and that is a pair of binomials consisting of trig functions. Anytime we see binomials, or a binomial squared, or a binomial times a trinomial, really any sort of parentheses, we should immediately think to ourselves, I need to multiply that out. So we're going to multiply this out. We're going to FOIL it. So we're going to do 1 times 1, which is 1. 1 times secant, which is secant. Negative cosine times 1, which is negative cosine. Negative cosine times secant, which would be negative cosine times secant. No real trick there. We're just going to write it out. Now we can make this a little bit better, not a lot better, if we realize that secant is 1 over cosine. Which means, if I leave everything else alone, I can replace that with 1 over cosine. So my algebra brain, again, should kick in and go, up, cancel, which would turn this into 1 plus secant minus cosine minus 1. Well, I don't know about you, but I'm fairly certain that I know what 1 minus 1 is. That's right, those would cancel, leaving me with secant minus cosine. And I can't really make that better, unfortunately. Okay, that brings us to 1 plus the tangent of negative theta over the tangent of negative theta. Alright, so we're starting off with a quotient here. That is a little bit of a problem. We're not allowed to have quotients in our final answer, so we know we have stuff that we need to do. Now, any time that we start off with a negative theta, our first step is to get rid of that negative theta using a negative angle identity. So the tangent of negative theta is always equal to the negative tangent of theta. So we're going to replace both the top and bottom tangent negative theta with negative tangent theta. That gets rid of the negative thetas and satisfies the first part of our, or second part of our directions, which says all functions are in terms of theta only. Okay? So then what we have to do is we have to write everything in terms of sine and cosine. So in both this case here and on the bottom, we're going to replace that tangent with our quotient identity, which says tangent is sine over cosine. So this is going to become 1 minus sine theta over cosine theta over negative sine over cosine. And I know what you're thinking, Mr. Wills, you're crazy. You just made the fraction into a bigger fraction and a more dangerous fraction. No, not really. Because anytime we have a fraction over a fraction, we simply can deal with that problem by multiplying the bottom and the top by the reciprocal of the denominator. So we're going to multiply the bottom and the top by the reciprocal of the denominator. Now keep in mind, that's protected. We're going to have to distribute on top. Okay? But on the bottom, all of this is the whole point of doing this, all of that will cancel. Okay? It's all gone. All of that is gone. So we're going to distribute. Now when we distribute a fraction, we distribute through the top and through the bottom. Now don't forget about this negative. It's technically is moved out front now. Okay, I almost screwed that up. We can't lose that negative. Okay? So we have negative, and then all that's left is on top, cosine over sine, this is negative, minus sine cosine over cosine sine. Now before we deal with the negative, let's make this better, okay? Our algebra mind again should kick in and go, all of that cancels, because that's one fraction, so I can cancel top to bottom, which means this term is 1. Over here, we should recognize this as being cotangent, which is cosine over sine. So right now we have negative cotangent theta minus 1. All we need to do to finish this up and make it a little bit better is distribute that negative through this parentheses, which is really like distributing negative 1, and would turn this into 1 minus cotangent of theta, because it would make cotangent negative and 1 positive, allowing me to switch them around. Okay. So, this next expression, we have some negative angles to deal with again. However, I want to point something out here, and that is what these things are actually saying. Okay? It doesn't really matter whether or not these end up being negative, because this notation is saying that we are squaring those cosine negative theta, tangent negative theta, which means it doesn't matter whether they're positive or negative. When we square them, anytime we square a negative number, it becomes a positive number. So even though this is actually negative tangent theta, when I square that, negative tangent times negative tangent is going to be positive tangent squared. So this becomes 1 minus cosine squared over 1 plus tangent squared. And those negative thetas kind of disappear because they're being squared. Now both the top and the bottom of that fraction are forms of Pythagorean identities. On top, if we rearrange our first Pythagorean identity, one of those forms was that sine squared is equal to 1 minus cosine squared. So we're going to take 1 minus cosine squared out and put in sine squared. On the bottom, 1 plus tangent squared is one of our Pythagorean identities, completely straightforward. That is secant squared. So we're going to take out 1 plus tangent squared and replace it with secant squared. Now, the only problem with that is that secant squared, we still have a fraction. So we need to apply one more set of stuff here. We need to say, oh, well, secant, that's 1 over cosine. Which means I can rewrite this again. We'll leave the sine squared alone and replace the denominator with 1 over cosine squared. Well, that's a complex fraction, so all we need to do to get rid of it is multiply by its reciprocal, which would be cosine squared. So we're going to multiply the bottom and the top of the fraction by cosine squared. Again, the whole point of that is that the entire denominator will cancel, and that will get rid of the fraction, giving us sine squared theta times cosine squared theta, which is as simple as this expression is going to get. All right, next up, again, we're doing a lot of examples. Secant minus cosine. I know what you're thinking, that's not that bad. Why mess with it? Well, because we can combine those two terms into one term if we do it the right way. So we need to change everything into terms of sine and cosine. So secant is 1 over cosine, which means we're going to rewrite this as a pair of fractions. 1 over cosine. I'm going to leave myself a little bit of room to work, and then I'm going to write cosine over 1 so that it's a fraction and we can see what we need to do. We need to get a common denominator to combine those two fractions. So when we do that, we need to multiply the second fraction by cosine to get a common denominator, which means we also need to multiply the top by cosine. That would give us 1 over cosine minus cosine squared over cosine. We combine those two fractions together using our rule for adding fractions, which is we really only combine the top. We turn that into 1 minus cosine squared, and that would be over cosine. I know what you're thinking, that's not really any better. It still has subtraction in it. Well, 1 minus cosine squared is one of our Pythagorean identities. We did this a minute ago. That's sine squared. So I can replace the top of my fraction with sine squared. Now, other than the fact that we have a quotient, we've managed to get this down to one term, which makes it simpler. But that's an easy fix as well. Keep in mind what sine squared means. Sine squared is telling us that we are multiplying sine times itself. So what we really have here is sine times sine over cosine. Well, that means we can take one of those sines and use it to get rid of the fraction, because tangent is sine over cosine. So we can substitute a tangent into that expression, giving us a final answer of tangent times sine. It's really more about practicing our manipulation here. It's all about working our way through what the common tricks are. So we've got a few more to do. Looks like 5 to go. I'm going to speed up a little bit here relatively soon. So here we have two pairs of parentheses. What should we do? We should multiply. So we're going to multiply this out. Secant times cosine is secant cosine. There's no trick to it. We just write them next to each other, indicating they're being multiplied. Secant times sine, negative sine, is negative secant sine. Cosecant times cosine is positive cosecant cosine. Cosecant times negative sine is negative cosecant sine. We should then go in and replace secant with 1 over cosine. And cosecant with 1 over sine. So that would look like this. So our algebra brain should kick in a couple places, right? Those cosines would cancel. These sines would cancel. Now also we'll combine those fractions on this step. That's 1 minus sine over cosine plus cosine over sine minus 1. So our algebra brain should kick in again and go 1 minus 1. That's nothing. That cancels. I'm also going to do some replacing here. I'm going to replace sine over cosine with tangent. And cosine over sine with cotangent. While I'm at it, I'm also going to switch them around so that the negative right here is on the right. So that would equal this term, which is cotangent, minus that term, which is tangent. Okay, we should see this and our algebra brain should go, I need to distribute. So that's exactly what we should do. That would be sine theta cosecant theta minus sine squared theta. We should then replace cosecant with its reciprocal. Cosecant theta is 1 over sine theta. So that would be sine times 1 over sine minus sine squared. Algebra brain, cancel the signs, which would give us 1 minus sine squared theta. That has come up a couple of times. It should trigger one of our Pythagorean identities and remind us that we're able to replace that with cosine squared. Okay, this one should be very quick, although you can make it very long if you don't do it the right way. As soon as we see the squareds, it should kick into our brains that that's probably one of our Pythagorean identities, and it is. That's secant squared on top, and this is cosecant squared. So your very first step should be to replace the top with secant squared and the bottom with cosecant squared. Then we should turn everything into sine and cosine. I'm not going to write that again because we should know that secant is 1 over cosine by now. We've done about 10 examples. And we should know that cosecant is 1 over sine. What does that tell us? Well, that means we need to multiply by the reciprocal of the denominator, which would be sine squared over 1. or sine squared. Again, the whole purpose of that is to cancel the entire denominator. That would give us sine squared over cosine squared. Well, sine over cosine is tangent. So that would be tangent squared, because sine over cosine is tangent. So sine squared over cosine squared would be tangent squared. All right, here we've got some negative angles again. We're almost done. But again, they're all being squared. We said earlier that it wouldn't matter that sine would turn into negative sine because it's being squared. That tangent turns into negative tangent because it's being squared. It also doesn't matter that cosine doesn't change because it's being squared. So what we end up with is sine squared theta plus tangent squared theta plus cosine squared theta. This one's a little hard to spot, but it's something that comes up all the time. We have a sine squared plus a cosine squared. It should trigger that if I add those together, the Pythagorean identities say that that is equal to 1. So that would be 1 plus tangent squared theta. And then that should trigger that secant squared theta is exactly that, 1 plus tangent squared. So we can then combine those two terms and turn this into secant squared, which would be our most simplified answer. Okay, cosecant over cotangent of negative theta. We would start by dealing with the negative angle identity there. So we're leaving cosecant alone for now. And we are changing cotangent of negative theta using the bottom negative angle identity into negative cotangent of theta. Now I'm going to write that negative out in front of my fraction for now, because my next step would be to convert cosecant into 1 over sine and cotangent into cosine over sine, and then rationalize, or get rid of the complex fraction. It's not the right word. Rationalize is not the right word. By multiplying the bottom and the top by sine over cosine. Again, the entire point being to cancel the bottom. We can also cancel the sine on top, which would turn this into negative 1 over cosine theta, and our reciprocal identities should tell us that that is equal to negative secant. That's it. That was the last example. So again, the second section worth of notes has already been posted. This is more for the people that are struggling with the homework 5-1. Hopefully you'll find this helpful, whether now while you're trying to finish your late homework or later on when you're studying for your final exam.